Next thing I need to talk about is an application of electron configurations. And we're going to do 3 of those, but today I will only be interested in the size of ions. Now, one of the problems with the size of atoms and ions is that the quantum theory took away our ability to know exactly where the electron is at any given time, which also carries with it the idea that we cannot tell then exactly what the size of an atom is because we don't know where the outermost electron is. So we have to play a trick on the system. The trick is a simple one, however. Let's suppose we need to know the radius of an aluminum atom. What's done is to use a diffraction method, which is beyond the scope of our discussion right now, a diffraction method to figure out how far apart the aluminum atoms are in solid aluminum metal. You can do that, and your book gives you a little feeling for how it works, but it's oversimplified. So the idea is this. If you experimentally get the distance between the centers of 2 neighboring or adjacent aluminum atoms, that distance turns out to be 286 picometers. If you want the radius of one aluminum atom, it's going to be half of that value, right? From here to here is 2 radii. So the metallic radius is 1/2 the distance. This is the distance between the nuclei, and the metallic radius of aluminum would be 286 divided by 2, or 143 picometers. So that allows us to determine the radii of metals. Of course, over 2/3 of the elements in the periodic table are metals, so that takes care of a bunch. What about the other ones? Well, the other ones have to be handled one by one. If we look at diatomic molecules, like dichlorine, those can be handled pretty regularly as well, or pretty straightforwardly. You measure the distance between the nuclei of the 2 chlorine atoms in Cl2 molecule. That turns out to be almost 200 picometers. You divide that by 2, and so the covalent radius of chlorine is about 100 picometers, pretty close. Now, variations in, and there's a table of these in your textbook, variations in atomic size can be thought of as involving mainly 2 factors. One of them is that as the outermost electron occupies orbitals of larger and larger principal quantum number, other things being equal, the atoms will be larger because the quantum number dictates larger orbitals. Okay? Larger orbitals mean larger atoms. So we can look, if other things are equal, at the value of n, and that can give us some guidance. The other thing is that atoms become smaller as the effective nuclear charge, Z effective, increases. Well, I better tell you a little bit about that. There's not too much in your book about it. The effective nuclear charge experienced by an electron in an atom is given by the total nuclear charge, which is Z, minus a screening factor, which represents how much the inner electrons screen that particular electron we're talking about. Remember we said that this was a factor in the energy of orbitals, the screening. Well, you could sort of look at this in a rough way, and that's all we really need to do. Z, the effective nuclear charge, is equal to the full nuclear charge minus the inner electron shielding. Well, in most cases, that is the shielding due to the inner electrons. And we just saw how to figure out how many inner electrons there are. Well, let's look at this and see if we can figure it out in terms of trends. That's what I'd like to do, trends. Down a periodic table group, each step, of course, adds a new shell. Now, there are variations in that, as we saw starting at the 4th period. It not only added a shell, it added part of the previous shell, 4s, 3d. Okay? Each step adds subshells of inner electrons then. That's a fair statement. And shielding, each one of those subshells of inner electrons shields all the electrons outside. Okay? If they spend most of their time closer to the nucleus, they cut off that wonderful feeling of electrostatic attraction that all the electrons have for the nuclei for these outermost electrons. So the outermost electron does not experience a full Z anymore. It experiences a Z minus the shielding due to the inner electron. Now when you go down, however, we're changing full steps at a time. So we're adding a number of electrons, or a number of protons to the nucleus, but we're adding a number of filled subshells of electrons as well. And the whole thing cancels, approximately cancels. The Z effective stays roughly the same as you go down the group. So why would the size of atoms change down a group? It's because the atomic radius changes due to increasing N. So if we looked at, let's say, lithium, sodium, potassium, rubidium, and cesium, the nuclear charge, the effective nuclear charge, doesn't change very much as we go down. But lithium's outer electron is 2s. And sodium's is 3s, and that's bigger than 2s. Potassium's is 4s, that's bigger than 3s. And so with the electron, the shielding not changing very much as you go down, then the value of N will make the difference. So there'll be an increasing trend in size going down. Remember that. Now across a period, electrons are added to pretty much the same outer level. And this is certainly true for the S and P groups. It's the same outer level. And these, since they're not down inside where the other electrons in that level are, they don't shield very well. So the electrons in that group, as you add a positive charge, each step you're adding a positive charge, you're adding an electron, the electron doesn't shield very well, so the effective nuclear charge goes up. And if the effective nuclear charge goes up, that squeezes the radius down. The higher it is, the smaller the radius is going to be. Look at this. This is a set of atomic sizes from aluminum over to argon. Well, thanks. Somebody likes to play little tricks. I'm sure they're gone now. Did somebody change this? No? Well, maybe it's the one on the other side. Oh, okay. Thank you. It wasn't a trick, it was an accident. Okay, so in going from aluminum to argon, we're putting electrons into one subshell, the P subshell. Which one? Well, you could think about that. So here are the trends in the periodic table. I'm going to write them with my pen, and I think it would be a good idea if you did too. The size variation in a period in the periodic table increases from right to left. These are the big atoms over here and the little atoms over here. Okay? And they increase down. The little atoms, bigger, 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 bigger. Okay? So the trend of size is increasing down and increasing from right to left. Oh, there we go. So increasing from right to left and increasing from top to bottom. Now, an exception here is the transition elements. Look at these transition elements. Look at scandium over to zinc. Well, it looks like they might be going down a little bit. The numbers are there for you to look at. But the change is not very much. Why would that be? Where are the electrons going for these elements? They're going into the 3D, which is one subshell down. So those electrons are going into the guts of the atom. And as such, you put a positive charge in, and you put an electron in that shields that positive charge. So the outer electrons don't feel much different. So as long as you put those electrons down into the inside of the atom in a lower shell, they're not going to cause very much different in the effective nuclear charge of the outer electrons here, which of course would be the 4s ones here. Okay? And it doesn't really make a big change as you go down either in the D subshell. The only real change, and the thing I'll leave you with today, is that the elements right after each one of the D subshells is filled, they're smaller than you would expect. They are smaller. If we look at boron, small, aluminum gets larger. Aluminum's 143 picometers radius. But then gallium drops down to 135. Okay? And the reason it drops is because we put 10 positive charges in here, and those 10 charges didn't shield perfectly. And this shows what it is. So gallium, then indium increases and thallium increases, but these elements are smaller than expected. Questions on that? Yes, go ahead. That's right. N is equal to 4 is higher than N is equal to 3. All right. 3 has a higher energy, but remember we fill from the bottom. We fill from the bottom. We get the 4s first. And I want to remind you that as far as the size of atoms go, the trends in the periodic table are, if I can have your attention please, are increasing from right to left across a period and increasing from top to bottom down a group. And so we can compare the sizes of atoms using those trends. So here is a problem. Using the periodic table, rank each set of main group elements, these here, these 4, in order of decreasing size. When you see decreasing size, the light ought to go on your head, say, I want to find the biggest one first, and I'll work down from there. Okay? So we've got calcium, magnesium, and strontium. And calcium and magnesium and strontium are here in group 2A. And what I like to do, and what's a very good practice, is to separate out a little portion of the periodic table that includes these elements and then use the trends on it. I'm going to find their positions in the periodic table like we just did and then consider the size trends. So let's look at these. Here's a little section of the periodic table. It includes group 1A, part of group 1A and part of group 2A, and here's calcium, magnesium, and strontium. And I remember that the trend is in size is increasing downwards, like so. So that would mean that the largest of these atoms is the one at the bottom. Strontium is the largest, and calcium will be next, and finally magnesium will be the smallest. So the ordering is strontium larger than calcium, calcium larger than magnesium. Questions? That's a one-trend comparison, so it's pretty straightforward. Let's look at the second one then. Potassium, gallium, and calcium. If we look at this, all 3 of these elements are in the same period. But there are some elements between them. But the trend in size is increasing from right to left, and therefore potassium ought to be the largest one, and gallium ought to be the smallest, and the ordering ought to look like that. So that's another single trend. Okay, pretty easy to do if you just set up the section of the periodic table where these elements live. If I look at the third one, you have bromine, rubidium, and krypton. Now here we have a 2 trend because bromine and krypton are in one period and rubidium is in the next period. Next period down. Okay? So the trends are for bromine and krypton that the size increases from left to right. And if we go over here to whatever elements in the same period as bromine and krypton, that element right here will be directly above the one. I want the one that's directly above rubidium, which of course will be potassium. So the size trends are increasing. Rubidium will be larger than that element, and increasing from right to left. Bromine and krypton will be smaller than that element, and krypton will be the smallest, rubidium the largest, so the ordering looks like this. Now it is true that you can find some combinations of elements that you can't compare this way, but we don't include those on homework or tests. Finally, strontium, calcium, and rubidium. Strontium, calcium, and rubidium. It's another, in this case, 2 groups. And if you look at those with the trend going towards the lower left, it seems clear rubidium will be the largest one, and strontium is 1 step smaller than rubidium, and calcium is smaller than strontium, so that will go like that. So that's my best advice into how to work these trend questions. Does anybody have anything they need to ask about that? Okay. Let's see any questions. So I want to talk about ionic size then. The size of ions is important. There's a lot of biochemistry that depends on ions for function, and the size of the ions can be quite important. The right size ion does a job, the wrong size ion causes a problem. So it's good to be able to compare the sizes. The standard definition of the radius of an ion is the size of the cation or anion measured in a crystalline ionic compound. This is done by diffraction, and diffraction processes will let you see the atoms, see the ions, see how far it is between them, and so forth. Most of what we need to recognize can be figured out from Coulomb's law. Cations are smaller than their parent atoms. Why? Well, because if it's a cation, it has more positive charges than negative charges. The atom has equal number of positive charges and negative charges. The cation has more positive charges. So what do you think that's going to do to the electron cloud? Going to squeeze it down, make it smaller. So cations are smaller than their parent atoms. Likewise, yes? I'm sorry? Well, I'm sorry. Write it down. I'm not sure. Does anybody see this slide? Oh, I must have put it in while I was asleep. I'm sorry. It's not that big a deal. Okay? It is there? It's just out of order. Okay. So cations are smaller than their parent atoms, and anions, well, before I go on to anions, here's a little graph that shows you the size of atoms and ions. For example, if we look at lithium, and you don't need to learn the radii. All you have to do is be able to compare the values qualitatively. If you look at lithium, it has 3 protons and 3 electrons. And the size of lithium is represented by this blue hemisphere here. Lithium with a single positive charge has still 3 protons, but now it has 2 electrons. And those 3 protons squeeze 2 electrons harder, and so the lithium 1+ ion is smaller. Okay? The parent atom is larger than the ion. And the same is true for all of these. You see the difference gets bigger as the charge on the cation gets larger. Okay, now let's go to the anions. Anions are larger than their parent atoms because they have the same number of protons, but the anion has more electrons. So the positive charge can't hold the extra negative charge as well. So if we look at this, here, for example, is fluoride ion. And the red hemisphere is fluorine atom. So fluorine atom has, what, 9 protons? And 9 electrons. The fluoride ion has 9 protons. And how many electrons? How many? 10 electrons. So the ratio is such that the fluoride ion is larger. There are, I have seen in the PCAT test and the MCAT test, there are frequently questions that say which one is larger. And just writing down the number of protons and the number of electrons will help you reason what that is. If you don't remember the rules, you can figure it out. Okay. Any questions about the relationship between the sizes of cations and atoms and anions and atoms? Okay, good. Now, ionic size increases down a group of comparable ions. Let's say lithium ion, lithium plus, sodium plus, potassium plus. Potassium is the largest one because the number of electron shells increases every time you step down the group. So ionic size increases down a group for the same reason that atomic size does. Right? So that's pretty straightforward, not a lot of trouble with that. But if you try to compare ions across a period, you immediately run into quicksand. And the reason for this is as you go across a period, the ionic charge changes and the number of protons changes. So you can have the number of protons and electrons both changing. Then you have very little to help in making comparisons. So we restrict what you're going to be exposed to here, in most cases, to those sets of ions, cations, that are isoelectronic, which means same number of electrons. So if we compare cations, all of which have the same number of electrons, we can get the relative size by looking at the number of protons. All right, let me show you how this works. Sodium ion, magnesium ion, and aluminum ion are all in one period, moving from left to right. And sodium has 11 protons and 10 electrons. And magnesium has 12 protons. Z is equal to 12 for magnesium. And 10 electrons. And aluminum likewise has 13 protons and 10 electrons. Now, if we just change the number of protons and keep the number of electrons the same, we're looking at isoelectronic cations here. And therefore, the ratio of the positive charges and negative charges will tell us what we need to know. And in this case, it says that 11 protons and 10 electrons compress the charge cloud less than 12 protons and 10 electrons. So sodium ion is larger, bigger radius than magnesium ion. And magnesium, likewise, is larger than aluminum ion. Aluminum will be the smallest because it has 13 positive charges squeezing 10 negative charges. Does that make sense? Question? All right, let's do the same thing for these anions. In looking at the anions, we have phosphorus. Phosphorus, if we look at the periodic table here. Here's phosphorus, sulfur, and chlorine. 15 protons, 16 protons, 17 protons. So this will have 15 protons. This will have 16 protons, sulfur anion, and chloride anion will have 17 protons. And this will have 18 electrons, this phosphide ion. Sulfide ion has 18 electrons, and chloride ion has 18 electrons. They all have the argon configuration. So in looking at this, it once again has the seeds of its own solution in there. 15 protons can't compress 18 electrons as much as 16 can. So phosphide is larger than sulfide. And likewise, 17 can compress more than 16. So chloride is the smallest one. There's not as big a difference in the anions, but the trend is pretty straightforward. So that's how you compare the sizes of isoelectronic anions. And over here we did isoelectronic cations. There's one other thing that we can do, and that is to look at the ions that form from one element. We said some of the transition metals form different numbers of ions, like iron 2 and iron 3. So when we look at that, if we look at iron 2 and iron 2 has 26 protons and 24 electrons. Iron 3 plus has 26 protons and 23 electrons. So iron 3 ought to be smaller. Its 26 positive charges can compress a 23 electron cloud more than a 26 can compress a 24 electron cloud. So for a given element or type of atom, the larger the positive charge on it, the smaller it is. Questions? All right. Then let's do an exercise. Rank each set in decreasing size. So we look at each set of ions here and find the largest one and then write the trend towards decreasing size. So we've got calcium, magnesium and strontium here to start with. They're all in group 2A, so the decrease in size up the group is expected. Strontium is the one at the bottom of the group, or lowest down, so strontium will be the largest one, and magnesium will be the smallest. That's the vertical trend, which works the same as it does for atoms. Okay, here are the sizes, so you can get a feeling for this. This is the gray hemispheres are the size of the atoms. The red hemispheres of the size of the ions, and you can see strontium ion is larger than calcium ion here. Okay, what about B? Potassium cation, sulfide anion, and chloride anion. How do we compare these? Well, the only way we've got to compare them is to see if they are isoelectronic. And fortunately, they are. K plus has 18 electrons, 19 minus 1. Sulfide ion, as we saw a little bit earlier, also has 18 electrons, has the argon configuration. And chloride ion also has 18 electrons. So as we look at these things, we have get my pen to work here. Potassium has 19 protons and 18 electrons. And as we said before, sulfur has 16 protons and 18 electrons, sulfide ion. And chloride has 17 protons and 18 electrons. So sulfide ion has the most electrons per proton, and so it's largest. And chloride ion is next, and potassium ion, potassium cation, will be the smallest. Questions on those? Okay, you're going to see a lot of those in the 18 homework. And I suggest that you think about ions in terms of positive-negative charge ratio. Your book doesn't make a big case of it, but I think it's an important tool. I think it'll give you an advantage. And the ionization energy, IE, is the energy needed to remove 1 mole of electrons from 1 mole of gaseous atoms, or maybe ions. So this is a process where you put energy into the system, enough energy to pull the least tightly bound electron out. I would like to ask you folks over there to either listen or leave. Thank you. The ionization energy, because of what I just said, is always a positive number. The process is always endothermic. And the first ionization energy is indicated by IE1, and it is the energy needed to remove the least tightly bound electron, the one in the highest occupied sublevel, from a gaseous atom. It has to be gaseous. That's IE1. Now, polyelectron atoms, if they start off with more than 1 electron, they can have more than 1 ionization energy. They can have the first ionization energy, IE1, and then if they have 3 electrons, they could have IE2 and IE3. But recognize IE2 will be taking electrons away from a cation. So that's going to be endothermic too, and it's typically going to be larger. So this is the equation that is used to represent the IE1 process. Atom in the gas phase goes to ion, positive ion, in the gas phase plus an electron. Delta E for that is equal to the ionization energy 1, and it's endothermic. IE2 is always, without exception, larger than IE1 for the same atom. And IE2 requires us to start with the ion that's produced in the first step and remove an electron from that ion to make now a dication. IE2 is always greater than IE1. Now, looking at periodic variations in IE1 is going to take more of your attention, because the trend, at least part of it, is not smooth. The reason that it's not smooth is because the variation in electron configuration will affect how much energy is required to pull an electron out. So this is a plot of the main group elements and their arrangement in the periodic table. I've left out the transition elements here. And the height of each one of the columns here is proportional to the ionization energy in kilojoules per mole. Now, part of this is pretty simple. The ionization energy is highest at the top of a group and decreases down the group for any group that you want to look at within the main group. It's usually true. But if you look at how it varies in a period, then all bets are off. And I hate to tell you how many students come up to me after the final exam and say, I missed this question on IE1 because I just used the trend that it goes across here like that. But notice, lithium goes up to beryllium, down to boron, up to carbon, up to nitrogen, down to oxygen, up to fluorine, up to neon. This is not a smooth trend. And if you're asked the question, which has the higher ionization energy, first ionization energy, beryllium or boron, and you think about the trend, you're going to choose boron, and that's wrong. Now, I want to say a little bit about why this is in a minute, but I want you to recognize that you can't just use the broad trends for changes like this. Now, this bumpiness of the line is most exaggerated in the the second period here. It's less exaggerated in the third period, and by the time you get down to the fifth period, it's gone. So it's most the second and the third, and a little bit in the fourth period where you see it. Now, I've plotted this in a different way over here. This is the first ionization energy versus Z. And what I'd like to point out to you is that there are two dips that occur, and I want to explain why they occur. When you go from lithium to beryllium, the ionization energy increases because the number of positive charges on the nucleus increases, and the shielding doesn't follow suit. But when you go from beryllium to boron, it goes down. Okay? And the reason for that is because the third element, the third electron that went in to form boron, to form boron is a P. It goes into a P subshell. Now, P subshells, we saw before, are above the corresponding S subshell. So that means you've already raised the electron part way up to being out of the atom, so it doesn't take as much energy to take it the rest of the way. So this is filling, and this is like S1, S2, and this is S2P1, and the S2P1 takes less energy to remove the electron than S2. The next dip is between nitrogen and oxygen. And when you think about this, nitrogen is a P3, S2P3. That's nitrogen right there. S2P3 is one electron in each one of the p orbitals, right? Parallel spins. When you go to S2P4, then you've got to put one electron in where there's another electron. And that makes that electron easier to remove. So from nitrogen to oxygen, even though the overall trend is up, that particular dip is due to the fact that we're taking away the outermost electron, which is in a p orbit. Questions on that? Okay, I hope you remember. We're going to rank elements according to the first ionization energy then, and we'll take the same kind of approach as we did before. We will use the trends where we can, and we'll cut out a little piece of the periodic table where the elements are and work from there. It's asking us for the order of decreasing, i.e. 1, so we need to look for the highest one first. And we have krypton and helium and argon. So I've put down a little piece of the periodic table here: helium, neon, argon, krypton. And our three elements are in there. The trend, if you recall, is that the ionization energy increases up the group. And so the highest one of these ought to be helium. And then we'll rank them down from there: helium, and then argon, and then krypton. Helium greater than argon, greater than krypton. Questions on that one? If you remember the trend, it's easy. And this is a vertical trend, and there aren't so many exceptions in there. The second one is antimony, tellurium, and tin. This is across a period, but it's the fifth period, so the bumps that we saw in the second period don't apply here. So we have antimony, which is here, antimony, and we have tellurium, and we have tin. Okay, the trend here in ionization energy is that it increases this direction. The tellurium ought to have the highest ionization energy. Right? So that trend. So tellurium should be greater than antimony, and antimony ought to be greater than tin. That's how we do that one. Okay. The next one is potassium, calcium, and rubidium. That's a two-trend. The two trends are increasing upwards and increasing to the right. And the elements are potassium here, and calcium here, and rubidium here. So in looking at this, which one of these ought to have the highest ionization energy one? It's rubidium, potassium, or calcium. Those are the ones. Calcium. It's going to be calcium, isn't it? Calcium is higher than rubidium, and it's to the right of potassium. So it ought to be the highest one. And so that means that we would work down from there. Potassium is next, and finally rubidium is lowest. Does that make sense to you? You have to have the trends, and sometimes it's just easy to remember that the general trends for ionization energy are backwards from size. If you can't remember, if you remember one of them, remember the other ones backwards, I guess that'll do. The last one here is iodine, xenon, and cesium, and these are elements in two different periods, but they're heavy periods, so we don't have to worry about the problems in the second period. We look at this, the ionization energy increases as we go up, and it increases to the right. So the highest one, it's pretty easy to see, ought to be xenon. Xenon should have a higher ionization energy than iodine, and then iodine will have a higher one than rubidium, which is right here, and rubidium would be higher than cesium. So cesium is the smallest one. You can use a kind of a dummy one in here for comparison purposes if you want. All right. Let's see here. What else did I want to say about that? Okay, I don't have anything else to say on that unless you have a question. If not, then what I would like to do is look at successive ionization energies. This is kind of tricky. I beg your pardon? I couldn't hear you. The microphone? Oh, where is it? Oh, you. Okay. I'm sorry. Go ahead. Too close to me.
Do you have to memorize the periods going across them if it is bumping?
She asked if you had to memorize the periods.
Yeah, the ones that go up and down, because it's not always, you say it's not always the same. Periods 1 to 3.
The second period and the third period for sure, those variations that I showed you in the third one and the sixth one, I would memorize them. The rest of them, all you have to do is learn the trend. If you don't want to memorize them, think about why they're there. The p orbital, the first electron in the p orbital is the reason for the first one. And the second one is the first pair of electrons in p orbitals is the reason for the second one. Okay, now if we think about successive ionizations, we have kind of an interesting process that goes on. You take out the least tightly bound electron first. That means the electron in the valence, right? Those electrons are the ones that are highest up in the manifold of the atom. If the atom is a tall building, they're up on the top floor. Okay? And if you take a case like lithium to start with here, lithium has Z is equal to 3, so it has 3 electrons. The valence electron in lithium is 2s1. So if you ionize lithium, the first electron to come out is the 2s1, and that's a valence electron, and that requires, according to this diagram, 0.52 megajoules. The next electron, once that electron is gone, the next electron is one of the 1s electrons. And those are core electrons, inner ones. It costs a lot more to ionize an inner electron because they are so much more stable in the atom. So look what happens. We go from 0.52 of a megajoule over 10 times higher when we take the first core electron. There's a huge jump right here, right? From 0.52 to 7.3. And then the next core electron goes up, but not as much. So as you look at these values here, if we go to beryllium, it has 2 valence electrons. So we have 0.9 for the first one, 1.7 for the second one, roughly, multiplying that's about twice. And then all of a sudden, it jumps not quite 10 times, but it jumps a whole bunch. The lesson to be learned, when you look at successive ionization energies, for example, for carbon, you have 1.09, 2.35, 4.62, 6.22, bang, 37.83. That's the first core electron. And if you didn't know it was carbon, you could at least figure out that whatever that fellow was, he had 4 valence electrons, right? Because you had 4 relatively low values going up a little bit each time, and all of a sudden it went through the ceiling. The ceiling was the first electron out of the core. Questions about that? This is a frequently missed topic. A jump occurs after all the valence electrons have been ionized. So, here we are. What element Q in period 3 has these ionization energies, and these are in kilojoules per mole? So, IE1 is 577. IE2 is 1816, went up about a factor of 3 here. IE3 is 2744. Okay. IE4 is 11,576. How many valence electrons does Q have? 3. So if it's in period 3, here's period 3, sodium, magnesium, aluminum, 3 valence electrons. Who is Q? It's aluminum, isn't it? It has 3 valence electrons, and the 4th one is a core electron. Start here, it's take away this one, and you take away that one, and you take away that one, and then the next one that goes is neon electron, and you pay dearly to get a neon electron out of there. Is this clear? Do you have questions? Okay. So Q is aluminum. And you could draw a line between the valence electrons and the core electrons. There he is. Okay. Now, in the minutes I have left, I want to introduce the last and the hardest of these. This is called electron affinity. And in a way, it's sort of like the reverse of ionization energy. Instead of taking an electron away from a poor atom, we're going to give that atom an electron, and we're going to figure out how much energy exchange occurs. Because it can be, we might get energy back if we give a certain atom an electron, or we might have to push the electron on it, depending on, what do you think it depends on? The number of valence electrons, in general, the electron configuration. So, first of all, here's the equation that represents the energy change. This is the thermochemical equation. An atom in the gas phase plus an electron goes to a negative ion in the gas phase. Delta E for that process is the electron affinity of that particular atom. And as I said, in some cases, energy is released, so delta E would be negative. And in some cases, energy is required, in which case delta E would be positive. So, to illustrate this, I want you to think about the carbon atom. The carbon atom is well known to us. It's a highly studied atom for all different kinds of reasons. If we wanted to write down the equation for the electron affinity of the carbon atom, it would be carbon in the gas phase plus an electron goes to C minus in the gas phase, right? Carbon in the gas phase plus an electron goes to C minus. All right. Now, there are, despite what the book says, there are very few, if any, smooth trends in electron affinity, because it is much more sensitive than anything else to electron configuration. So it's going to leave it to us to see how electron configuration influences this. And it boils down to a pretty simple thing. What we're going to do is we're going to look at the electron configuration of the anion, and we're going to look at the electron configuration of the atom, and we're going to use the principles that we have about the stability of electron configurations and determine whether we are going downhill or uphill in stability. So here's carbon. I'm going to write down here that carbon valence electron configuration is 2s2, 2p2. Box diagram, pair of electrons here. And a blank one right there. Okay? And we're going to add an electron to this atom. And so what is the valence electron configuration of the carbon anion? Tell me. 2s2, 2p3. If I write the box diagram for this, look what it is. Exactly half-filled p subshell for C minus. Do you think that that's more stable than carbon atom? I think so too. Yes?
Is it Hund's rule?
Is it, pardon me?
Hund's?
Hund's rule, he asked if this is Hund's rule. It's Hund's rule to determine what the electron configuration is, but it's the exchange energy from quantum mechanics that tells you it's more stable. This is really two things. Okay, so a half-filled subshell is more stable. So that means we're going downhill. So the electron configuration of the carbon anion being more stable means that the extra energy in going from up here down to here is released. And in fact, the electron affinity 1 for a carbon atom is negative 122 kilojoules per mole. And that proves that its electron configuration is more stable than the 2s2, 2p2 configuration. So the smooth trends are absent. We look at the stability of the anion to compare electron affinity values. And the last thing I'll tell you is the second electron affinity is never negative. It's always positive. We were discussing electron affinities. And we said that electron affinity represents the process by which an atom in the gas phase accepts an electron to produce a negative ion in the gas phase, and the electron affinity is the delta H for that process. So electron affinities can be negative, or they can be positive, or they can even be zero in a few cases. They're pretty close. And what we said, using carbon as the example, has an S2P2 configuration. If you add an electron to an S2P2 configuration, that electron has to go into the P subshell, and carbon minus in the gas phase has what electron configuration? Valence. S2P3. Is P3 more stable than P2? Sure it is. It's a half-filled subshell. And therefore, we went from carbon, which was a less stable configuration, to carbon minus, which was more stable in terms of its electron configuration. So we said that's the reason that the electron affinity for carbon is exothermic, and it's pretty negative. We went from a less stable to a more stable configuration. Now, if you look at the main group of the periodic table, here, group 1A is an S1 configuration. So the electron affinities are pretty negative, pretty exothermic, not as the biggest ones you ever saw, but they're all negative, and they're fairly sizable. The reason for that is that the electron affinity will be S1 goes to S2. S2 is, for the anion, is a stable filled subshell. And so you're going from a less stable configuration to a more stable configuration, so these have negative values, exothermic. 2A is an S2 configuration, and it's going to go to an S2P1 when we add an electron to it. And S2P1 is less stable than S2 because the electron that went into the p orbital went up higher in energy. So these elements, these atoms, have electron affinities which are pretty close to 0 or might even be positive in some cases. If you look at the group 3A to 4A to 5A to 6A, you have a P1, a P2, a P3, P4, P5, P6. So we know something about the stability of partially filled P subshells, don't we? We know that a P3 is a stable half-filled subshell. And we know that a P6 is an even more stable filled subshell. So as you look at these values, this is S2P1, S2P2, this is S2P3. So if you look at these values, boron is negative but not very big, exothermic but not huge. Carbon, as we saw before, is exothermic and large. Nitrogen already has a filled, half-filled P subshell, and therefore, in going from nitrogen to nitrogen minus, we're going to the S2P4 configuration, which is less stable. More stable to less stable. These electron affinities, well, nitrogen's positive and the others are negative but not huge. And so forth and so on. We have S2P5 here, which is one electron short of a noble gas configuration, S2P6. So these elements in group 7A, being S2P5, are only one electron short of the grand finale here, the electron configuration of the noble gases, which are among the most stable that we know. And therefore, these have large negative values of the electron affinity. And the elements in the 8A column already have a stable filled electron configuration here, filled S and filled P. So they have very unfavorable electron affinities because the next electron's got to go up here into the next S subshell. Questions on the grand scheme of things in the main group? All right, so I remind you, if you have questions that have you compare electron affinities, you achieve the answer by comparing the stability of the electron configuration of the atom versus the ion. Okay, now I've redone this slide just a little bit in terms of these examples. So it says, without looking at figure 8.20, pick the atom in each pair with the most exothermic electron affinity. So we have X, which is an NS2NP2, or Y, which is NS2NP3. Okay, so we have X plus an electron goes to X minus. And X is NS2NP2, S2P2. And X minus is S2P3. So X minus is more stable because of its electron configuration, P3 here, and therefore its electron affinity is exothermic. If we look at Y, Y is S2P3 already. We add an electron to Y, we get Y minus, this is all in the gas phase, which would be S2P4, right? S2P4 is less stable than S2P3, which is more stable. So if we go from more stable to less stable, that means we're going uphill. And therefore, the electron affinity is not exothermic. It's probably endothermic. Questions on that choice? Yes?
Do you know that P4 is less stable than P3?
We know that because we said P3 was a special case of a very stable half-filled subshell.
Because they're all parallel?
Because they all have parallel spins. That's right. Other questions on this? All right, I'll let you do Z and Q. Now, from the middle of page 325 to 327, I'm going to leave mainly for your own study. I'm not going to spend much time on it. I just want to mention a couple things. The group 6A and 7A atoms, as we saw in the previous slide, have negative or exothermic electron affinities. And being to the right of that period, they have large ionization energies. So these mean, these two things together mean that these atoms have a favorable process for adding electrons to them, and therefore it's reasonable that they would form negative ions. So these would be things like oxygen and fluorine and sulfur and chlorine. Groups 1A and 2A, on the other hand, have low ionization energies because they're on the left side, and either negative or positive electron affinity. And the low ionization energies mean that most likely they're going to form positive ions. Yes?
Is Q or Y more stable?
Is the electron configuration of Q more stable than the electron configuration of Z?
Yes.
Well, you tell me. S2P6 versus S2P5. Which one do you think it is?
Q.
It's
talking
Q.
about Q or Y, right?
Oh, Q or Y? Oh, I'm sorry. I misunderstood what you said. A filled subshell is more stable than a half-filled subshell by a nickel or two. Okay, so group 1A and 2A tend to form positive ions. Well, that's no news to us. We already knew that, but this kind of explains a little bit energetically why. The noble gases have very high ionization energies because they're extremely stable electron configurations make it so. And they have endothermic electron affinities. So the high ionization energies mean they're not likely to form positive ions, cost too much energy to take an electron away from them. And the endothermic electron affinity means they're probably not going to form negative ions because there's nothing to be gained, and maybe even you have to put energy in. So these guys don't form positive or negative